I wanted to work through the practice test for test 1. This is the test that's covering all the material from the start of the semester until test 1. So that was work on electric charge, electric forces, electric fluxes, electric potential, electric fields, and then also work on electrical circuits, electrical circuit components, capacitors, resistors, and circuits with capacitors, resistors, and batteries. First question. 2 identical glass rods are rubbed with a silk cloth. After rubbing, and then it's questions about whether the glass rods attract or repel one another, whether the glass rods attract or repel the silk. When you rub a glass rod with a silk cloth, electrons are transferred, rubbed off, scraped off the glass rod onto the silk cloth. And the glass rod becomes positively charged and the silk rod will become negatively charged. And so when we rub 2 glass rods with the silk cloth, then the 2 glass rods become positively charged and the silk cloth is negatively charged. That means that the 2 glass rods, because they're like charges, they're both positive, they repel one another. Whereas the glass rods will attract the silk cloth because they're oppositely charged. So glass and silk will attract, glass and glass will repel. Okay, second question. Let's go on to this second question. We've got 2 negative charges, Q1, Q2. They're separated by 1 centimeter. We're told that the second charge, Q2, is bigger in size than the first charge. And we're asked to compare the forces on Q1 and Q2 and the fields at the locations of Q1 and Q2. And we're asked to consider whether the forces are the same size, different size, the fields are the same size or different size. So the forces between the 2 charges, that's a pair of forces. Charge 1 exerts a force on 2 and charge 2 exerts a force on 1. So that pair of forces are going to be equal and opposite sized forces. So the force magnitudes are the same. I'll just write down forces are the same, but I mean the force magnitudes are the same. What about the fields? The fields are going to be different. So the field of charge number 1, which is the smaller of the charges, will be smaller because it's a smaller amount of charge, creating that field at the location of the second charge. The field of charge number 2, that's going to be larger. It's a larger field at the location of the first charge. And so the fields are different. So although the forces are the same, the fields are different and the charges are the same. The force, if you remember, is related to the field through this definition here. And so if the forces are the same, but the fields are different, then the charges must be different, which is the case. Third question. We've got 3 charges on the sketch. There's 2 negative charges, different sizes, and 1 positive charge. And then we got 3 surfaces, closed surfaces on the sketch, and they're labeled S1, S2, S3, F4. And we got we've got to examine the fluxes through the different surfaces, and in particular, which fluxes are zero. So the key thing about if there's a net zero flux through a closed surface is that the total charge inside that closed surface must be zero. If the charge inside a closed surface is non-zero, then there is a net flux through the closed surface. And if it was positive charge, it would be a positive net flux coming out. If it was a negative charge, it would be a negative net flux. That's flux going in. So let's look at our sketch here and see which fluxes are zero. The most obvious one is probably S4. Here's S4. Now, although it's in the neighborhood of charges, there's no charges inside that surface S4 whatsoever. So that has zero flux. S4's flux is zero net flux. Then maybe the less obvious one is S2. Here's S2. That contains charges, but look, it contains equal and opposite amounts of charge. So overall, it's electrically neutral. Overall, the charge inside it is zero. So that one too has zero flux. The other two surfaces, actually, if you look at them, you see that they both have net charges inside of them. So the correct answer to this problem is that the net flux through S2 and S4 are the ones that are zero. Okay, question number 4 on the exam. In this question, we're asked to compare two circuits. We've got circuit A, that's on the left, and it's got two light bulbs in parallel connected to a 1.5 volt battery. And circuit B, that's the one on the right, it's got two light bulbs in series, and that's connected to the terminals of a 1.5 volt battery. And we're told that the two batteries are the same and the 4 light bulbs are the same. And we're asked to compare the current that is drawn from battery A and the current that is drawn from battery B. And the question is asking how many times bigger is the current from battery A than it is from the current from battery B. One way we can answer this is to think about the equivalent resistor that is across the battery in circuit A and the equivalent resistor across the battery in circuit B, and how much power is drawn by those two equivalent resistors. In the case of circuit A, we've got two resistors in parallel. And so 1 over the equivalent resistor is 1 over the resistance of the upper lamp plus 1 over the resistance of the lower lamp. And so the equivalent resistor is actually, if you take the inverse of the left-hand sides and right-hand sides here, it's the resistance of one light bulb, R, divided by 2. So that's circuit A's equivalent resistance. Let's look at circuit B's equivalent resistance. Circuit B, the equivalent resistance, well, these resistors are now in series. So the equivalent resistance is just the sum of the individual resistances, the resistance R of the left-hand and right-hand light bulbs. So in that case, the equivalent resistance is 2R. And so if we compare circuit A and circuit B, the resistance of circuit A, the two resistors in parallel, is actually 1/4 of the resistance of circuit B. So now we know the resistances, R over 2 or 2R, we can figure out the currents using Ohm's law and knowing that the resistor networks are connected across the terminals of identical 1.5 volt batteries. So over here on the left-hand side, let me write down Ohm's law there. We got V, which would be 1.5 volts, equals the current flowing in the left-hand circuit, I'll call it IA, times the resistance of the left-hand circuit, and that's R over 2. And over on the right-hand side, we've got the applied voltage, 1.5 volts again, will equal by Ohm's law the current in the right-hand circuit times the resistance of the right-hand circuit. That's 2R in this case. Well, look, if the V's are the same, but the R's differ by a factor of 4. So the resistance of circuit A is 4 times smaller, or the resistance of circuit B is 4 times bigger. The current for circuit A must be correspondingly 4 times bigger than the current for circuit B if the resistance of circuit A is 4 times smaller than the resistance of circuit B. So the current supplied by battery A is 4 times the current supplied by battery B. Okay, question number 5. Equal potential differences, so equal potential differences delta V, are applied between the plates of the 3 parallel plate capacitors. Compare the magnitudes of the charges on the plates. So let me first just start by writing down the relationship between charge, voltage, and capacitance. Here it is as the definition of capacitance. In this case, it's more useful for us to think of the charge on the plates being equal to the capacitance of the capacitors times the voltage difference between the plates. Now, what we know is the voltage differences are the same for each of the parallel plate capacitors. But the capacitances, because of the different geometries, they're going to be different. So the capacitor with the biggest capacitance will have the most charge. The capacitor with the smallest capacitance will have the smallest charge. Think about the equation for the capacitance of a parallel plate capacitor. So it's permittivity of free space times the area of the plates divided by the separation of the plates. So big area makes a big capacitance. Small separation also makes a big capacitance. C2 is going to be the biggest capacitance. I can see that because, well, it's got the same size plates as C1, but it's got a shorter separation between the plates. So this will make its capacitance bigger. I can see it's also clearly bigger than the capacitance of C3 because C3's got smaller plates. That makes the capacitance smaller, and it's got a bigger separation. So it's definitely bigger than C3. If I now compare C1 and C3, well, C1 has got the same separations as C3 between the plates, but C1 actually has twice the area, which increases the capacity to store charge. So C1 is going to be bigger than C3. So if this is the ordering of the capacitances, by this proportionality between capacitance and charge for the same applied voltage, then Q2 must be biggest, Q1 must be next, and finally Q3 will be smallest. Okay, question number 6. So in number 6, we're given a graph or a plot of the electrical potential versus position X. and we're asked to figure out the electrical field at a certain location or a certain position of 1.5 centimeters. So the field, electric field, is the negative slope of the electrical potential. We can write that as an equation. The equation would be E equals minus delta V, the change in potential, divided by delta X, the change in position coordinate. To find the field at this point, 1.5 centimeters, let's think about this region of space here from 1 to 2 centimeters, where the potential is constantly changing. Let's figure out the field in that region, and then that will be the field at the point 1.5 centimeters. So the change in the field, that's the final change in the potential, that's the final potential minus the initial potential. That's going to be minus 30 volts. The negative sign is because the potential decreased. And then the change in position from upstairs here to downstairs here, that's 1 centimeter. So that's 0.01 meters. And so if we divide the numerator by the denominator, the signs cancel out, and we get 3,000 volts per meter. And that is answer here. Okay, question 8 says, calculate the electrical field at the midpoint between the two charges in the sketch below. And we got a positive charge on the left and a negative charge on the right. So here is the midpoint, 2.5 centimeters from both charges. And if I was to draw the fields, well, the field of the positive charge points away from the positive charge. It might look like this. The field of the negative charge points towards the negative charge, so it might look like this. And I've drawn them with relative sizes, relative magnitudes, that indicate that the larger charge produces the greater field, the smaller charge, the smaller field. And then if I was to add these two vectors up, I'd get some resulting vector that might look like this. Now, there's an important point here. The fields are vectors. They have sizes and they have directions. In this particular case, it's relatively simple because the two fields are both in the positive X direction, both towards the right. And so those two fields just add together. And so if we want the total field, in this case, it's just going to be the magnitude of the total field. It's just going to be the magnitude of the field due to charge number 1 plus the magnitude of the field due to charge number 2. The magnitudes of those fields for each individual field of each point charge depends on the Coulomb constant, the magnitude of the charge, and the square of the distance from the charge to the field point. And the same thing for charge number 2, the Coulomb constant times the size of the charge times the divided by the square of the distance from the field point. So the Coulomb constant is a common factor. Let's pull that out front. And then we just got to multiply Q1 over R squared. Sorry, we just got to add Q1 over R squared plus Q2 over R squared. So that would be 6 nanocoulombs. Coulombs, I won't write the units. Divided by the square of this distance, 2.5 centimeters, so 0.025 squared. And then we've got to add on to that the contribution from the other charge, the magnitude of this charge, that's 2 nanocoulombs, 2 times 10 to the minus 9, divided by the square of its distance, which is also 0.25 centimeters. And that's our equation for the electrical field strength. And if you calculate that, I got approximately 113,000 newtons per coulomb. So that's the answer to that question. Okay, next question, question number 9. We're told we got an electron. It's accelerating at 5.7 times 10 to the 13 meters per second squared. And it's accelerating an electric field. And we got to calculate the magnitude of that electric field. So we're told the acceleration. Let's start from that. The acceleration of an electron or any object, any mass, is going to be the force acting on it divided by its mass. That's Newton's second law. The force acting on it in this case, because electrical force, is the charge of the electron times the electrical field it's immersed in. And so here's a relationship between the field that we want and the acceleration that we know. If we turn it around, this is an equation that says that the mass of the electron times the acceleration of the electron divided by the charge of the electron will give us the electrical field. So all we need to do is to plug in the various numbers here. So downstairs here, here's the mass. Also downstairs here, here's the charge. And upstairs here, here's the acceleration. And so I just plug in A, M, and Q. I won't write down all the numbers. If I do the calculation, the result that I got by plugging in the mass, the acceleration, and the charge was 324 newtons per coulomb, or volts per meter. That's the size, that's the magnitude of the electrical field. Okay, question number 10. We're told we got a cube. It's 1 by 1 by 1 centimeter cubed in volume, and it contains a total charge that is minus 0.15 nanocoulombs. And we're asked to figure out the net flux or the total flux through that cube. Well, this is a question about Gauss's law. Gauss's law tells us the net flux through a closed surface, the cube is a closed surface, in terms of the charge inside the closed surface. So in this case is the net flux, and Gauss's law tells us that the net flux through that cube is equal to the charge contained inside the cube divided by epsilon naught, the permittivity of free space. So in this case, we've got minus 0.15 nanocoulombs of charge. We've got a permittivity of free space. It's 8.85 times 10 to the minus 12. And if you divide the charge by the permittivity of free space, I got a number that was minus 16.9. The units come out to be the units of field times the units of area. So Newton meter squared over Coulomb. So the answer to this question is minus 16.9 Newton meter squared per Coulomb. Okay, question number 11 says that we have a parallel plate capacitor with a plate separation that's 2 millimeters. And we apply a potential difference, 1.5 volts, between the two plates of the parallel plate capacitor. And we got to calculate the electrical field that exists between the plates of the parallel plate capacitor. Well, the electrical field is the negative slope of the electrical potential. And so if we know the electrical potential difference across the plates, and we know the separation between the plates, that's the delta V, that's the delta X, we can calculate this electrical field. Now, in this case, we just want the magnitude of the electrical field. So we won't worry about the direction of it. So the magnitude is just the magnitude of the potential difference. That's the 1.5 volts, divided by the separation. That's the 2 millimeters. So we got 1.5 volts divided by 2 millimeters is 0.002 meters. And if we divide those two numbers, I got 750 volts per meter as the electrical field between the plates. So the answer here is 750 volts per meter. Okay, question number 12. In question number 12, we got two charges, a positive 6 nanocoulomb charge on the left, a negative 2 nanocoulomb charge on the right. We are told that we move the right-hand charge by 1 centimeter further away from the left-hand charge. And we've got to figure out how much work we do in joules. So these two charges are attracting one another. And to separate them further from 5 centimeters to 6 centimeters, we need to pull them apart, push them apart. We need to do some work. So we're going to do some work. And the amount of work that we do as we push these charges apart, so this is the work I'm going to do, is going to be the change in stored electrical potential energy. So the arrangement with the charges further apart will store more electrical potential energy than the arrangement of the charges when they were closer. And so I'm going to have to add that extra energy by transferring energy by doing work. The amount of energy I add is the difference between the final potential energy and the initial potential energy of the two charges. And we can write that in terms of the potential of the left-hand charge at the location of the potential of the right-hand charge. So the right-hand charge is Q2, and its final potential energy will be its charge times the potential it's sitting in. So that's the potential created by charge number 1 at the final position, and its initial potential energy was its charge times the initial potential that it was sitting in. And so this equation tells us the work done in terms of the charge we moved and the potential we moved it from, VI, to the potential it ended up at, that's VF. Now it's just a matter of filling in the equation for the potential of a point charge so that we can fill in VF and VI. So let me just do that. I'm going to collect together some common terms when I do that. Here's the equation I get. So the Coulomb constant was a common term in the expressions for the potentials of the point charges. So was the charge of the left-hand charge, Q1, a common term. And we already had a common term that was Q2, the charge of the right-hand term. And so this expression is the work that we're going to do. And we just need to fill in all the numbers. 9 times 10 to the 9. I won't write in the units, save time. Charge number 1 is plus 6 times 10 to the minus 9 coulombs. Charge number 2 is minus 2 times 10 to the minus 9 nanocoulombs. And then we've got 1 over the final position, so that's 6 centimeters or 0.06, minus 1 over the initial position, that's 5 centimeters or 0.05. And if you do this calculation, this comes out to be 0.36. It's 0.36 microjoules, 10 to the minus 6 joules. And so that's the answer to this question, 0.36. And you notice it is a positive number. Though we had a negative charge, because we pulled the charges apart, the work that we did was positive. The system stores extra electrical potential energy. Okay, question number 13. It says 4 identical point charges, each of 2 nanocoulombs, are located on the vertices of a square, 1 centimeter by 1 centimeter. And we got to calculate the potential, the electrical potential at the square's center. Let's just make a sketch of that to start with. I'm going to draw the 4 charges. Here they are. As I say, they're located on this square where the sides have length A. And we want the potential at this point here, the very center, due to these 4 charges. I'm going to call them all Q because they're all the same. And the other thing that's important in this problem, that's the same for all the charges, is the distance to this field point or this potential point. Now, the distance from one corner to the opposite corner by Pythagoras, well, that's the square root of a squared plus a squared. So it's the square root of 2 times a. So this total distance from the top left to the bottom right is the square root of 2 times a. Now we want half that. That's the distance to the field point. So half of the square root of 2 times a is actually a over the square root of 2. And each charge is that distance from the field point. Okay, so now we can write down the potential at the field point due to the 4 charges. What's that potential going to be? What's the equation for that potential? Well, the potential of a point charge, let's just think of one of the charges, say this top left point charge. Its potential at that location is going to be the Coulomb constant times its charge divided by its distance from that field point, and that's A divided by the square root of 2. So that's the potential of the top right charge, top left charge. But all the charges, all the other charges are the same values at the same distances, so they all contribute that. So the total potential is 4 times kq divided by a over the square root of 2. And so we can just plug in now k, q, and a. We know all these numbers. The charges are 2 nanocoulombs. The distance a is 0.01 meters, and the Coulomb constant 9 times 10 to the 9 Newton meter squared per Coulomb. I'm not going to write in all the numbers. And I calculated a potential that is 10,183 volts. And so that was my answer to question number 13. Okay, question 14. In question 14, we've got a a light bulb with a tungsten filament. It's a thin wire inside an old-fashioned light bulb. We're told that that filament, which is like a resistor, it acts like a resistor. That filament has 120 volts potential difference across the ends or terminals of the filament, and it dissipates a power that is 40 watts, 40 joules per second. And we got to calculate the resistance of the filament, or the resistance of the light bulb. So to do this calculation, I thought about, well, we know power and voltage, and I thought about the relationship between power and voltage. So here's basic relationship between the power dissipated in a resistor like a light bulb and the voltage and the current across and through the light bulb. Now in this place we don't immediately know the current, we do know the voltage. And so I just used Ohm's law to replace the current in terms of the voltage and the resistance. So V equals IR, or I equals V over R. So we get V squared over R. Now, if we look at that equation, it contains the power, something we know, 40 watts. It contains the voltage, something we know, 120 volts. And it contains the resistance, the item that we want. And so I just rearranged it, that the resistance of the tungsten filament is going to be equal to the square of the voltage across the filament divided by the power. And I filled in 120 volts, squared that, and divided by 40 watts. I got 360 ohms. And so 360 ohms is the answer to that question. Okay, problem 15. Problem 15, we're going to work out the equivalent single resistor that represents this circuit of 4 resistors, where the 4 resistor network has parallel components, series components, and we're going to use the rules for combining series resistors, parallel resistors to solve this problem. I'm going to give the resistors some names. Here's R1 on the left. Here's R2 on the right, upstairs. Here's R3 downstairs. And here's R4 on the right. And so let's go ahead and combine these. Now, the first stage I did was to spot these 2 parallel resistors, combine those to make an equivalent resistance. And then I was able to spot 3 series resistors and combine those to make the figure the final equivalent resistance. So those are the two steps. So this step here, I'm going to make the equivalent resistance of the 2 parallel ones. I'll just call it R23. And this final step here is going to be the equivalent resistance of the entire network. I'm going to call it R equivalent. Now, because the 2 resistors R2 and R3 are in parallel, the equivalent resistance is related to those individual resistances by this little equation here, that the inverse of the equivalent resistance is the sum of the inverses of the individual resistors. And if you plug in 4 ohms and 7 ohms, you find that R23 is going to be smaller than any of the individual resistors. It comes out to be 2.54 ohms. So that's R23. Now we want the final equivalent resistance of the entire circuit. Well, now, once we've replaced R2 and R3 individually with R23, we've just got a circuit that has in series R1, R23, and R4. And so the equivalent resistance for a series circuit is just the sum of the individual resistors. So it's going to be R1 plus R23 plus R4. So it's going to be 4 ohms plus 2.54 ohms plus 9 ohms, and that all comes out to be 15.54 ohms. And so that's the answer to our question here, 15.54 ohms. Okay, the final problem, the fully worked out problem, where we show all our equations, diagrams, calculations, is problem 16. So in this problem, we've got a tiny charged sphere that's attached to a string. And the charged sphere is placed in a horizontal electrical field. And so the charged sphere is actually experiencing both a downwards gravitational force and a horizontal electrical force. And so it doesn't hang vertically downwards on the string, rather it hangs at an angle on the string. And the question is all about the forces that are involved as it hangs on the string and figuring out the angle at which it hangs on the string and how that angle would depend on, for example, the sphere's mass, or the another example would be the sphere's charge. Okay, so first part of the question says sketch the forces acting on the sphere. So let me first just sketch the sphere on the string. Here it is. I've drawn it at an angle theta, because as I say, I know because it's pulled downwards by gravity, but say to the right by electricity, it's going to be hanging at an angle. Now, what are the forces acting on this tiny charged sphere? Obviously, gravitational force. We'll just call it Fg. Obviously, electrical force horizontally. We'll call that Fe. And finally, so that the forces are balanced, so that there's equilibrium, there's the tension force. And that tension force will have components, horizontal and vertical components. This angle to the horizontal, to the vertical is also theta, just like this angle up here. And so there's a component opposite the angle. This is T sine theta. And there's a component of tension adjacent to the angle that's T cosine theta. So that's a force diagram. We're asked to calculate the electric and gravitational forces that are acting on the sphere. Well, let's do that. The gravitational force is just the mass. That's the quantity that experiences gravitational forces times the acceleration of gravity. The mass, we're told in the problem, is 5 grams. That's 0.005 kilograms. Multiply that by 9.8 meters per second squared. This comes out to be 0.049 newtons. So that's the gravitational force. Electrical force, well, that's just the charge times the electrical field. So the total charge of the sphere, we're told in the problem, is 40 microcoulombs. The electrical field is 150 newtons per coulomb. So multiplying those together, we get a force in newtons of 0.006 newtons. So those are the two forces. That's parts B and C. Now we've got to calculate the angle of the string. And to do that, I'm going to write down the equilibrium condition for the three forces that are acting, the tension force, the force of gravity, and the electrical force. So get my notes here. So we've got equilibrium. In the horizontal direction, there's a balance between tension to the left and the electrical force to the right. And so I'm just going to write down the relationships between the magnitudes of the tension and the electrical force based on that balance. So here's the magnitude of the tensional force to the left, and here's the magnitude of the electrical force to the right, and they must be equal in size. They're opposite in direction, but they're equal in size. So that's like equation number one. And then for the vertical component of tension, so it's T cosine theta, is balanced by the downwards gravitational force. And again, I'm referring to the magnitudes of gravity here and the magnitudes of the vertical component of the tension. They're in opposite directions. So that's like equation number two. Now, if you look at those two equations, you say, well, I don't know tension, but we can cancel out tension. If we simply divide the upper equation 1 by the lower equation 2, what do we get? The tensions cancel out if we divide them, and we just get sine over cosine, or tan theta. And tan theta will equal simply the ratio of the electric and gravitational forces. And so the ratio of the electrical and gravitational forces is really telling us the angle, or determining the angle. If I take the inverse tangents of both sides, the angle itself is just the inverse tangent of the ratio of these forces. And if you plug in 0.006 newtons divided by 0.049 newtons, take the inverse tangent, you get about 7 degrees, 7.0 degrees. And so that's the answer to part D. Finally, part E says, if the sphere's mass is increased, does theta increase, decrease, or remain unchanged? If the mass goes up, suppose we increase the mass, that means that we're increasing the gravitational force. It means that we're reducing this ratio of forces of electricity to gravity, which would decrease theta. So if the mass goes up, theta goes down. On the other hand, if the charge was to go up, the charge goes up, that increases the electrical force, which increases this ratio of forces, which would increase theta. So that's just how the angle is dependent on the two forces, and the two forces themselves are dependent on the properties of that sphere, its mass and its charge.